Hi Level 3s and welcome to your second tutorial for the further assessment opportunity for 3.7 redox. Today we're covering galvanic cells, so let's just get straight into it. So galvanic cells are spontaneous, which means if you put these two things together they will produce electrical energy, which we measure using a voltmeter. The species with the highest reduction potential always gets reduced. And if there's a metal involved, so if we're talking about copper or zinc, then that will become the electrode. If we don't, so if we're talking about aqueous solutions, so let's say we're talking about permanganate and permanganate ions, or manganese ions, neither of those are in the metallic form, so therefore we will use an inert electrode. Okay, so I have put up an example and I'm going to draw the cell and we're going to talk through it now. So I've asked you to create a cell between zinc and iodine. So we can start by doing the template of our cell. So we plug in a voltmeter there instead of a power supply because these produce electrical energy. This time slightly different because in two beakers, okay? Connecting the two beakers to make sure that, we've got a complete circuit as a salt bridge. And we soak it in potassium nitrate. The rule with the salt bridge is that cations go towards the cathode, so your K plus will go this way, and your anions will go towards the anode. So always label your anode on the left and put that anode as the site of reduction. That's something that stays the same in both types of cells, and your cathode is the site of reduction. Electrons flow from the anode to the cathode. So that is the template for all galvanic cells. I haven't even put any details about what we're doing right now. So that's just our template. We can still actually add to this. We can now put the charges. The charges flip for these cells, so the anode is negative and the cathode is positive. We say that the anode is negative in this case because it's a spontaneous reaction. This is the source of electrons, so is negative, and this is where electrons are getting consumed, so positive. Okay, so the next thing that we've got to do now that we've got our template is decide what is getting oxidized and what is getting reduced. And you can see here on the left I have put the reduction potentials. These will be provided to you in your assessment. Species on the left are your oxidants, because these are always written as reduction. So I2 is getting reduced to I minus, zinc 2 plus is getting reduced to zinc. So it's really important you understand they're always written as reduction. So if these species are getting reduced, that makes them oxidants, and these species, therefore, if they got reversed, these would be reductants. So the species with the highest reduction potential get reduced. So this I2 is the strongest oxidant compared to zinc. Okay, so that means I2 will get oxidized, and therefore the species with the lowest reduction potential gets oxidized. You have to flip these reactions. So in order to oxidize this bottom one, you actually have to flip it and start with zinc, and so therefore zinc is the strongest reductant in this case. So we can use that information and now start going on with our cells. So if we start with, for instance, the oxidation reaction, so you can write your oxidation reaction. Zinc solid forms zinc 2 plus 2 electrons. Okay, now because zinc's a metal, it will be the electrode, so that anode is going to be made out of zinc metal. And when we do a galvanic cell, you must have both species present, which means you must have zinc 2 plus and zinc present. Zinc's present as the electrode because it's a metal, so zinc 2 plus must be here in aqueous solution. Now technically speaking, you can't have a positive ion without a negative ion, so I'm just going to chuck a spectator ion in there. Sulfate's a really good negative one, so is nitrate, so pick whichever one you find easier. So zinc sulfate in this case is the electrolyte. We've got zinc ions, we've got zinc metal. Okay, this is the reaction that's happening. Oxidation number of 0 and plus 2. Increase in ON equals oxidation. Loss of electrons equals oxidation. So let's now talk about reduction. So reduction, we're starting with I2 and we're producing I minus. Okay, there's going to be 2 of them. And so therefore to balance the charge, we add 2 electrons to the left-hand side. Electrons being gained is reduction. Oxidation number of 0, oxidation number of -1, a decrease in oxidation number equals reduction. Okay, so this time I2 and I minus, neither of them are metals, and therefore they cannot be the electrode. So they're just both going to be in solution. So we'll have I2 aqueous, okay, but we'll have an equal amount of I minus. And so I minus aqueous will also be in here. Now I2 is fine as it is. I minus can't really exist like that. So you could also write that as Ki aqueous. Okay, so potassium is a good positive spectator ion if you need one. So we've got both species present, because remember I said that was one of the requirements. You must have I2 present and I minus. The reason why they're both in solution is because neither of them are metals. So that means we still need to state what this electrode will be made out of, and if it can't be a metal, it's going to be platinum or graphite, an inert electrode. Okay, so let's just go through this again. So we've got our oxidation half cell over here. So this is all oxidation and this is reduction. Okay, during oxidation, zinc's going to get oxidized to zinc 2+, and we know this because zinc has the lower reduction potential and therefore it will get oxidized. Electrons flow from the anode to the cathode. I2 is getting reduced, and we know this because it's got the higher reduction potential. Neither of these are metals, and so therefore they'll both be in solution. I2 / I minus, or instead of I minus you could do Ki, because I minus doesn't exist on its own. So here are the half equations, and then you could go and do a full equation, but I'm not going to bother. You guys can do that for now, and we'll practice those in the tasks. What we can do is calculate the cell potential. So the E0 cell is reduction minus oxidation. So what's getting reduced is I2, so it's going to be 0.53 minus 0.76, and we're going to get a value of positive 1.29 volts. Because that's positive, the reaction is spontaneous. The other thing that we do that is just for galvanic cells is we can actually draw what we call a cell diagram, which is actually a shorthand notation of this big diagram that we've just drawn. To do that, we do oxidation first. Okay, and metals or solids or electrodes go on the outside. This vertical line is a phase boundary between solids and anything else. In other words, an easy way to remember it is put your electrodes on the outside. So there's zinc metal, okay? And apologies here, I forgot to do states, which we always must do. Okay, so zinc, and then we've got zinc 2+. A double line in the middle stands for a salt bridge. And then we do reduction here. Now, the reduction one, neither of the two species are actually the electrode. So we know that the electrode is going to be platinum or graphite. So you can just pick whichever ones. Electrodes go on the outside. So here we need to put both species involved in the reaction, reduction reaction, and do it the order that it happens. So I2 forms I minus, so we do I2 first. So I2 aqueous, we do a comma, and then we do I minus aqueous. So the comma is to say that there's no change between aqueous and solid. Okay, so the comma is for anything. It can be aqueous and gases here. So we just put a comma between these two species. So hopefully that makes sense. We're going to jump on and do another example now. Okay, so this time we've got dichromate and lead. So we start off with our normal template. Okay, your two cells, the salt bridge of KNO3, K plus goes down here, nitrate goes down here. Electrons flow from your anode to your cathode, so cathode is the site of reduction. Anode is the site of oxidation. Anode is negative, cathode is positive, and so far we've got our nice template. So now let's add in our example. We look at which species has the highest reduction potential. In this case, it's dichromate. So dichromate is getting reduced because dichromate is the strongest oxidant. Okay, so here's our reduction half cell. So inside here, we need to have Cr2O72- aqueous, and we also need to have Cr3+ aqueous, okay? Neither of these are in the metallic form, which means this electrode must be inert, so it's going to be platinum or graphite. We know that neither of those can actually exist like this because they do need to have a spectator ion, so you might have it as K2Cr2O7, 2- needs to be balanced out by the 2 K pluses, and you might have chromium nitrate in there as well. Okay, so That's technically what you should have in there. I've drawn my diagram a bit small there, but you could do arrows coming out like that in your internal if you needed to. Okay, so that's the electrolyte. So over this side, we've got lead and lead 2+. Now, because lead, this couple's got a lower reduction potential, that means it's going to be oxidized. And when that happens, we have to start with this species and form this species. Because remember, these are always written as reduction. So if we're oxidizing them, we have to reverse the species. Never reverse the sign here. We just reverse the species. So lead is in fact a metal, so lead will be the electrode in this case, and so we have Pb2+ aqueous in the electrolyte. Again, we can't have positive ions without negative, so lead sulfate would be a good one here. You could also do lead nitrate. So now we've actually worked out what's happening, we can do some equations here. So if we do the oxidation one, that's nice and easy. Pb solid goes to Pb2+ aqueous plus 2 electrons. All metals are grey, so lead's grey, and Pb2+ ions are colourless. Okay, so let's now do, this has got an oxidation number of 0 and +2. Increase in On equals oxidation, and we also know that a loss of electrons is oxidation. Let's do the reduction half equation, and I will go through this just to make sure everyone can do it. So Cr2O7 2- aqueous goes to Cr3+ aqueous. First step of balancing half equations is to balance all other atoms except for oxygen and hydrogen first. So you've got 2 chromiums here, so we need to put a 2 here. You've got 7 oxygens here, so we need to add 7 H2O here. H2O is a liquid. In doing that, you've now added 14 hydrogens, so you need to add 14 H+ here, and H+ is an aqueous state. And the final step is to balance the charge. 2- here from dichromate. 14H+, that makes an overall 12+ on the left hand side. 2 times 3+ on the right hand side gives an overall 6+, so we need to add 6 electrons to the left hand side to balance the charge. Dichromate is orange, you must learn this, and Cr3+ is green. These are 2 colours that you will have to learn, and I'll show you a summary of colours probably in part B of this lesson, because I don't think I'm going to squeeze it in. We need to work out the oxidation number of this. The Cr2O7 2- is a polyatomic ion, so therefore the charge has to equal the charge on the ion. Oxygen's our known, it's -2. -2 times 7 equals -14. What plus -4 equals -2? And the answer is +12. There are 2 chromiums, so +12 divided by 2 equals, oops, it's gone funny, +6. So the oxidation number of chromium and dichromate is +6. It then forms Cr3+, which is a monatomic ion, and so it forms just the charge. You forget the 2 there, it's just the ion there. So therefore the oxidation number, there's a decrease in On, and that shows us that it's reduction. Okay, so quite significant colours here, but the key thing when you're doing your galvanic cells is that the species with the highest reduction potential is the strongest oxidant, and it'll get reduced. Species with the lowest reduction potential, that's the one that's going to get oxidized. And you can just do all of your half equations as per normal. If your reaction involves a metal, it will become the electrode. If there's no metal, we use an inert electrode, platinum or carbon. Okay, the only thing that I haven't mentioned here, which I will, is the fact that because lead metal is getting oxidized during this reaction, you would actually see a mass decrease with the electrode, and that's considered one of the observations. So you would not only have to say that it's grey to colourless, but you'd also have to say that the mass is decreasing. Okay, so that's quite important, mass is decreasing. If you have any questions, pop them on Teams about that, but I'll be back in a second with part B of this video.